All right, we got to get started because the other class we went right to the end. And you guys have even more questions than me. We're in trouble.
Or not.
Yes, we are. Because today's lecture is like the most intense of the lectures. And it's the last of the lectures. And also, don't forget, Monday is the first quiz of the year. It's going to cover logic 1 and logic 2. And since it's the first quiz, I made it kind of on the easier side. Okay, number 1. Did you guys learn from number 1? Okay, let me just tell you what you should have learned from number 1. Well, last time, didn't we learn that if you have a conditional statement, this is the example I showed you guys, right? It's logically equivalent to what? The contrapositive. That's important. But also, it's logically equivalent to something else. Now, in problems A, B, C, D, and E, which one came out to exactly the same truth table as P implies Q, which is true, false, true, true? B, it was D. No, it was E.
Oh, but
In fact, look at your answer for E. Look at it right now. Does it say true, false, true, true? So when you made that truth table, didn't you go, ding, hey, that's the same thing as the conditional? Or did you go, I'm just going to the next problem? That's the problem. I don't write problems where you just do busy work. I write problems where you're going to learn something. So as soon as you did problem E, ding, that's logically equivalent, not P or Q. So you can change a conditional to an or an or to a conditional by simply negating the first and leaving the second one alone. That's the pattern. I will box this. Now you don't have to write this down. You know why? It's in the notes. It says important equivalent statements. That's there. I wouldn't put it down if it's not important. And then what did you guys notice about problems 1A and 1B? What did 1A come out to? Here, let me think. True, true, false, true. What did B come out to? True, true, false, true. A, they're the same. So if two statements have the same truth table, they are logically equivalent. So what did you learn about in problem 1A and 1B? The conditional statement is logically equivalent to its contrapositive. Isn't B the contrapositive of A?
Yeah.
Yeah, so it's the same thing. It doesn't matter. It doesn't matter what form the conditional statement is in, the contrapositive is logically equivalent. Okay, now we can do number 2. What is this? What does this mean? What is that?
2D.
And then what's this thing after it? That's a comma.
Yeah. Well, obviously.
How can a comma be bigger than the letter? Look, the comma is bigger than the D. Okay, funny, I thought that was comical. Okay, 2D. Okay, very good. Now, if you couldn't do 2D, that means you didn't learn from number 1. Or you didn't look at the notes. Okay, so in problem 2D, you are given not Q implies P. Write the negation of it. How do you negate a conditional statement? Well, when you did problem 1D, P and not Q, what did the truth table come out to? Wait, don't tell me. False, true, false, false. Wait. Everybody look at 1D. Did it come out to false, true, false, false? Okay, as soon as that happened, what did you go? Hey, you somebody. No, you just skipped to the next problem. Look at this. False, true, false, false. Is that something we know? Or is it the opposite of something we know? Yeah, this is the opposite of true, false, true, true, which is the conditional statement. So if two truth tables have exactly the opposite truth table, then they are negations of each other. So if you want to negate a conditional statement, that's how you do it. It's an and statement. Leave the first one alone, negate the second. Yeah.
Is that the same for everything? Just leave the first one alone?
No, this other one is you negate the first one and leave the second one alone.
Why?
Because they came out to the same truth table.
Well, you have to do the truth table to figure that out.
Yeah, when you first learn it, but after you learn it, like when you first learn addition, how did you learn addition? Okay, 2 plus 3 is 1, 2, 3, 4, 5. But then after a while, you just go 2 plus 3 is 5 because you know it already, right? You don't reinvent the wheel, right? No, I like to reinvent the wheel, Mr. Park. So, do you guys understand? These two statements are negations of each other because they have opposite truth tables. So if you want to negate a conditional statement, it's an and statement. So if I want to negate this, it's an and statement. And how do I do it? Leave the first one alone and negate the second. Boom!
Is this in the notes?
No, that one
Well, it kind of is, but you have to make connections. Did anybody make the connection here? Okay, what is the connection?
I read it to or and it
Oh, somebody did! That's good. I'm impressed. Okay, this is what he said. He said a conditional statement is logically equivalent to an or statement, right? How do you do that? And what do you do? Negate the first and leave the second one alone, right? You following? Look.
Yeah.
Look, just look at these two. You just negate the first, leave the second one alone. So if you want to negate a conditional statement, you have to negate this. How do you negate an or statement? Can I just distribute the the not? Yeah, but you got to switch the or to and. So if I want to negate this, you get that, bam! Okay, so Mr. Park, let me understand this. In order for me to get this, I have to know which statements are logically equivalent to which exactly. Exactly. That's why in your notes it says some important equivalent statements. Do you guys see that in the notes? That is important. That's why I said important, because it's important. Because if you don't know which statements are logically equivalent to each other, you cannot do things like this. Then you just have to memorize all these different things, and then why memorize 50 things when you only have to memorize 4? Because I'm good at memorizing, Mr. Park. Okay, you guys get it? Or you can just simply memorize. If you want to memorize, you can. The negation of gorilla implies banana is gorilla and not banana. It's up to you. Okay, so now do we know how to negate a conditional statement? Yes, it's an and statement. The negation of a conditional statement is an and statement. Now, every single year on the first quiz, I'm telling you this so you don't make this mistake. Every single year on the first quiz, there's always like 10 to 15 people, you know what they do? The negation of a conditional statement is another conditional statement. It is not. It's an and statement. Okay, here, let me give you an example, because this is on the quiz. It's on the quiz, and you just have to be able to do it. Let's do different letters then. How about M implies not N? What is the negation of that? So if this is statement Q, what is not Q? What is the negation of that? M, and, what? Oh, I thought you were saying and. I thought, never mind. I thought when you're saying and, you're saying and. There it is. Can you guys do that? The negation of gorilla implies banana is gorilla and not banana. But like I said, why do you want to memorize that when you can just do this? Change this to an or statement. How do you change a conditional to or from this? Negate the first, leave the second one alone. So if you want to negate that, you have to negate this. Now how do you negate this? You distribute the negation sign and you get M and N. Boom! I don't care how you do it. If you're going to just memorize or you want to reason it out, I don't care. As long as you got that on your paper, you're fine. So, on Monday, what if I change this to like a A and a B? Is that going to throw you off?
Yeah.
Okay, then you're going to get thrown off then. Okay, now, if you couldn't do problem 2D, then you couldn't do number 3, right? Okay, look at problem number 3. Write the negation of the following statement. Hey, that statement is a conditional statement. If something, then something. If something, then something, right? So how do you negate that? What did we just learn? What is the negation of a conditional statement?
Leave the first
So,
one.
okay, box and
Negate.
not triangle. It doesn't matter what the words are, you just look at the form. So in problem number 3, look, it's a conditional statement. So what's the negation of that? Look, if box, then triangle. So what's the negation of that? Box and not triangle. So 2 to the p minus 1 is a Mersenne prime, and this thing is not perfect. You guys get it? The negation of a conditional statement is an and statement. Now, before we even move on, how do you determine whether the original statement is true or false? First, you got to know 2 things. You guys know what a Mersenne prime is? No, not anything. Not anything. And then, do you guys know what a perfect number is? Okay, so let's discuss that, because who knows? It might show up on one of these quizzes. Okay, so if p is a prime number, then is 2 to the p minus 1 also going to be a prime number? Oh boy. Is there such thing as a formula that generates prime numbers? The answer is no. You cannot. There is no formula that, if there was a formula that generated prime numbers, you'd probably be the most famous mathematician on earth. But there is none. However, sometimes it is. So if 2 is the smallest prime number, what is 2 to the 2 minus 1? 3. Is that a prime number? So if you plug in a prime number for p and you get a prime number, this is called a Mersenne prime, named after the mathematician Marin Mersenne. He was a French monk that dabbled in mathematics. That's why we named it after him. Okay, what's the next prime number? 3. What is 2 to the 3 minus 1? 2 to the 3rd? Oh, come on, people. 7. Is that also a prime number? Yes. So if you plug in the prime numbers and it comes out to a prime number, then that number is called a Mersenne prime. Okay, let's just do one more. What's the next prime number?
5.
5. If I plug in 5, what is 2 to the 5th minus 1?
31.
31. Is that a prime number? Do we really have to think about that? The answer is yes. So therefore, this is a Mersenne prime. Okay, let's just do one more for funsies. 7. 2 to the 7th minus 1. 128 minus 1. 127. Is that a prime number? Okay, see, you guys have the same problem as the other class. Okay, let's go back to elementary school. Let's say you're in a Turkish prison, or you're in your classroom. If you want to go to recess, you better tell me if this is prime or not. 50-50 chance. How do you determine if a number is a prime number? What do? You try and divide it by prime numbers. So, does 2 go into 127? Some of you are thinking really hard, yeah? Come on!
No.
Okay, no. What about 3?
No.
How can you tell if a number is divisible by 3? You add the digits, right? So no. What about 5? Okay, definitely. What about 7?
No.
How can you tell?
Divide.
Just actually divide it. What if the number is super huge? 500 digits long, what are you going to do? It's going to take a long time. Yeah, there is a method. Do you know it?
Plus and minus.
I forgot what it was. Okay, next one. 11. Does 11 go into that?
No.
How do you know? There is a divisibility test for 11. That one I know. Okay, let me teach it to you. Where is there? Okay, here. Suppose you have the number 5,736,412. Is that number divisible by 11?
No.
Here's the test. Starting with the first digit, add up every other digit. What is 5 plus 3 plus 4 plus 2? 14. Now, starting with the second digit, add every other digit. What's 7 plus 6 plus 1? 4. Oh, it comes up to 14? And then if you subtract them, if this number is divisible by 11, then the whole number is divisible by 11. Is 0 divisible by 11?
Yeah.
Yeah. So that number is divisible by 11. That's the divisibility test for 11.
Mr. Park, you figured that out?
No, kindergarten, I think you taught me. I can't remember if it was kindergarten or preschool.
Okay.
So does 11 go into that? No, because look, 8 minus 2 is 6, not divisible. And then what's the next prime number? 13, then you try 17. So when you check for a prime number, where do I stop? Do I just keep on going? 19, 20, tell me when to stop. 25, 27, 29, 31. When do I stop?
When you hit the half.
Hit the halfway mark. What's the halfway mark? 64. Then we're not there yet, then we gotta keep going. Come on, the other class knew. Anybody? No, stop with this online business. Okay, when you check to see if this number is prime, you keep checking for divisibility with the prime numbers, right? When do I stop? Just go until I get there then.
Oh, until you get the.
Yeah, so tell me, when do I stop? What number do I stop at? I'll tell you, right there. You know why?
Oh, because.
You just have to test until the square root of that number. What's the square root of 127? 11 point something. So once you test up to 11, you don't need to test anymore. No. Why does that work? Because factors come in pairs. Every time you have one that's above the square root of that number, isn't there going to be one below that? So that's why you only have to test up to the square root of that number. This is elementary school! No, I mean not this, but that's the topic is. Okay, now what are we trying to do? Now we're just trying to determine what a Mersenne prime. You guys understand what a Mersenne prime is? If P is a prime number, you plug it into this, and you also get a prime number. That number, so all of these are Mersenne primes. Okay, so it says, if you have a Mersenne prime, which is this, then if you multiply it by 2 to the P minus 1, that is a perfect number. Now the second question is, Mr. Park, what's a perfect number? We only can write on this side of the board in this video. Okay, what is a perfect number? Do you guys know? If you were in my summer school class, I taught you, right? There you go. The smallest perfect number is 6. That's because what if what are the divisors of 6? 1, 2, 3, 6. What are the proper divisors of 6? Proper means doesn't include itself. 1, 2, and 3, right? What happens when I add them together? You get 6. See, it comes out perfect. The proper divisors add up to itself. We called it a perfect number. What's the next perfect number? 28. What are the proper divisors of 28? Well, what are the divisors of 28? 1 times 28, 2 and 14, 4 and 7. Take away the 28. What happens when you add these numbers up? You get 28. See, it's perfect. What's the next perfect number? Come on, look over there. You guys don't notice things. Look at you guys see the perfect number eye chart right there?
496.
See, look. 496.
You did that by heart.
Yeah, I know. I can't even see that far at this age anyway. 496,
Oh, that's
8,128, 33,550,336. I just have the first 5 numbers. But I'm sure, at least you guys should know the first 2 of these. Anyway, these are perfect numbers. You guys want to try? Just for fun? What are the factors of 496? 1 times 496, 2 times 248. Does 3 go into that?
not for ready.
Okay, not for yeah. Anyway, if you were to add up all of these numbers, it would come out to 496. That's why it's perfect. See, now this is scaring me because now you know what a perfect number is. What about the number 8? Is 8 perfect? No, because it's not on the eye chart, right? But what are the proper divisors of 8? 1 times 8, 2 times 4, take away the 8. What happens when I add this up? You get 7. It's not 8, so it's not perfect. However, if the proper divisors add up to less than that number, we say that that number is, somebody impress me.
Less than perfect.
Yeah, but there's a word. Deficient. Deficient. I'm not making stuff up, people. I'm just relaying the information to you. Like, what about the number 12? What are the factors of 12? 1 times 12, 2 times 6, 3 times 4. Take away the 12. What happens if I add up these numbers? It's bigger than 12. So therefore, we say that 12 is?
Sufficient.
No. This one is deficient. This one is abundant. Doesn't it make sense? Abundant. because its factors add up to bigger than itself. But if it adds up to smaller than itself, we say that it's deficient. See, that's why I'm here to fill in all the holes. See, you go through your math career. There, this is your math career, except get holes all over the place. Some of you, the holes are like bigger than the area itself, yeah? So it's my job to fill in these holes. Anyway, so getting back to now that we know what a perfect number, now we can do this problem. See, the reason why I put these problems on so that you guys learn math. But no, I'm just going to go to the next problem and pretend it doesn't exist. Anyway, so what if P is 2? This is 3. What if I plug in 2 there? What do you get? 2 to the 2 minus 1. 2. Now what happens when I multiply these two together? You get 6. Is that a perfect number? Oh, yeah! Okay, what about this? If I plug in 3 into this, you get 7. What if I plug 3 into this?
4.
You get 4. What's 7 times 4? 28. Is that perfect? Oh my gosh! Okay, what about 5? Plug 5 into this, you get 31. Plug 5 into this? 16. What's 31 times 16? 496. So, if this is a Mersenne prime, and I multiply it by this, will you always get a perfect number?
Yeah.
Well, it worked for these first 3, therefore it's going to work for all of them.
Yeah.
Well, that's not thinking logically. It rained the last 3 days, therefore it's going to rain today. I got a present the last 4 days, therefore today I'm going to get a present too. No, that is not a proof. Okay? So, it worked for the first 3. Anyway, did anybody even look it up? At least the other class, they Googled it.
What?
This thing. If this is a Mersenne prime and you multiply it by this, the answer is yes, you will always get a perfect number. You know why? Because it was proved by, the other class knew because they looked it up. This class, what? You went to sleep. It was proved by
Euclid.
Euler. Euler. Leonard Euler actually proved that. If you have a Mersenne prime in this form and you multiply that, you will always get a perfect number. Always. How many Mersenne primes are there? Yeah, there's infinitely many, but so therefore there's infinitely many perfect numbers. But see, the problem is they're so huge you can't really tell. So you need computers to work on that. All right, now we can move on. Oh, we're in trouble, I can tell already. Next, number 4. Are we doing number 4? Yeah, number 4. Find a statement whose truth table comes out false every time.
It was in the first problem.
Yeah,
There's one
you-
that came
you
out
took
to true.
Okay, very good. Now this is what the clever people do. I don't know if they're clever, but this is what some people do. They did problem 1G.
Yeah.
What happened in problem 1G? Didn't it come out true?
Oh.
So if you just put a negation in front of it, then it will be false there. How many people did that? Okay, then the rest of us, we just came up with our own, yeah? Okay, what did COC, what did you get?
Oh,
COC.
do I have to say it?
Yes.
Okay. I don't know how to say it though.
We gotta learn.
Okay. Negate,
Not.
P and Q. Oh, well, if,
Quantity.
yeah, quantity.
Quantity.
Then quantity P or Q.
Okay, let's see if this works. P
Oh,
and
no, I mean like you negate the whole thing.
negate the whole thing.
Double
Everything.
print.
Oh, this, like that.
Yeah.
Okay, P or Q is true, false, correct? P or, no, this is and. This is true, false. P or Q is true, false. So this implies that is true, this implies that is true, this implies that is true, this implies that is true. So you negate the whole thing, you get false. Very good, it works. Well, okay, if you do something with a, okay, the key here is conditional. If you want something, the only time a conditional statement is false is when the first one is true and the second one is false. So all you gotta do is make sure when this is true, you gotta make sure that one's true. That's all you gotta do. So you got, in other words, in order to do this kind of problem, you gotta know how the statements work. If you don't know how they work, then no, it's very difficult to do it, yeah? So then you better just rely on, I did problem 1G, it came out true. I just go put a big negation in front of it. But then what about the quiz and the test? Do you think you're gonna have something there that comes out true all the time and then I'm just gonna put a big negation in front of it? You can pray. No, you gotta know how things work. Which brings us to problem 5. Are we doing 5? Yes, because this is pretty much everything, yeah? Now number 5, I put that problem there.
And more.
I put the problem there so that you would learn something. That's why, that's why I like to write my own problems, because you learn something. It's not just busy work. Okay, number 5. Okay, I can't even see that far. I'll attempt. Not R if and only if P and S implies not Q or S, which implies Q and R if and only if not P for video and not S. Did I copy that correctly?
Yeah.
Okay, now this is what I want you to do. Now what does it say about R? It says R is true, so what is not R? False. And what is P? True. So if you have a biconditional statement and they're different, then what is this? False. Okay, good. And then, do I even need to know what S is? No, I don't even need to look at S, because if you have an AND statement and one of them is false, doesn't that make the whole thing false? Because the only time an AND statement is true is when they're both true. Now, how many people actually figured out what all of this is? Okay, see that there, you didn't learn. Look, if you have a conditional statement and the first part is false, it's true already.
Oh.
That's what I wanted you to do. That's why I made the second part so massive, to teach you a lesson. Yeah, to learn.
To learn.
Oh, so Mr. Park, when I do homework, I need to think. Yes! What do you do when you do homework? You just do blah, 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 I'm done.
Get through it. That's all.
Get through it, okay. No. No! Does everybody understand what I'm talking about? If you have a conditional statement, if the first part is false, you know it's true already. Because the only time a conditional statement is false is when the first one is true and the second one is false. Therefore, it has to be true.
That makes sense.
Exactly. I should have, you know what? To teach next year's class a lesson, I should make this like doubly long, yeah?
Yeah.
Just make like 3 lines of it.
Yes.
Yes.
Oh, and then see the rest at the website and then accept more.
Yes.
Okay, did we learn from that now?
Yeah.
Okay, good.
I feel like if it was that long, everyone would just start looking at the bottom.
I want to
Because
get
they
their
wouldn't
dropout
want
slips out.
Yeah, no, you gotta do
Yeah.
that to them.
Stop saying things like that. Come on, do people actually just look at the bottom and write it down?
No.
No, see? No. And then finally, number 15. There is no number 15.
Yeah.
Is that a joke? Is today April 1st? No. What is 15? Or did you actually mean 14?
I think that means
Okay.
Number 1.
Okay, wait. No, okay, do I need to do 14? Okay, how many people, how do you show that these networks are equivalent? How many people made a truth table for this and made a truth table for that and then they came out the same? Okay, now what about the rest of us? Lie?
Oh,
I did the one.
Then how come you didn't raise your hand?
I forgot.
This is not raising hand. Okay, how many people did something different?
Do the ones and zeros count as?
Yeah, you can use ones and zeros. 1 is true, 0 is false. Actually, when you do networks like this, you should use ones and zeros. But I would accept F's and T's. Because it's... Okay, nobody did anything different. Okay, so we gotta learn. Number 4. Okay, shall I not teach you then? And on the and then on the test, you just take 10 minutes to do a 1-minute problem? Okay, here we go. Okay, so number 14, you have to show that these are equivalent. So let's symbolize number 13. I hope it not P or is that a Q? Gets ended with not Q and R not. Correct? Did I do that correctly?
Yes.
Of course, I'm your teacher. And then the other one is Q or, and you got not P gets ended with not R. There, did I do it?
Yeah.
So instead of making truth tables, because why do I want to make an 8-line truth table here and an 8-line truth table there? Why don't we use things we learn?
Oh, that's what you meant.
I said something different.
I did that.
Too late. Okay, did we learn like something that's logically equivalent to this?
Yeah.
Yeah, logic 1. So turn back to logic 1.
Wait a second. Yes, we did.
Okay, I'll show you. I gotta scroll them.
You.
Why did I give away my smart board? I had a smart board, and they convinced me to get a smart TV instead. No. Now every time I want to scroll, I gotta come back here. Turn your attention to problem 15 and 16. Didn't 15 and 16 come out with the same truth table? Yeah, we talked about it in class. So look at that. So if this has exactly the same form as 15 and 16, so what is logically equivalent to this? Look at that thing. Look, it's the same form, just the letters are different. What is this logically equivalent to? Q or not P and Q or not R. Hey, Mr. Park, it's starting to look like that.
Oh my god.
Now, when you have gorilla or banana, is that the same thing as banana or gorilla? Can I switch it? Think about it. When you make the truth table, does it matter which side it's on? No. So I did that. And then here's and. Now, what would happen if you have this, but I factor out a negation sign? What if I factor out a negation sign? What are you going to get? Not Q and R. It's the same thing like that. Finished.
Oh my.
No, I like making two truth tables that have 8 lines. But see, that's part of the learning process. It doesn't matter if you take 10 minutes or 1 minute, you still will get -0 on the test. Isn't that the goal? And don't worry about the length of the test, because I am giving exactly the same test when as 20-something years ago, when the classes were only 40-something minutes. It's the same test except you get 55 minutes. So you're getting like 12 more minutes to take the same test they took. So don't worry, if you take a long time, don't worry about it. Okay, now we got, today is the last lecture of the chapter. See, aren't you good? Aren't you glad you're in honors? Because, you know, in regular, it takes them 2 weeks to go through logic. We go through it in 3 days. That's the difference. Probably your friends that are in pre-calculus regular, they're, my guess, they're probably just making truth tables for P or Q and P and Q. That's my guess. That's what they're probably doing now. I'm not dissing them, I'm just showing you how advanced we are. No, I don't know why you guys laugh. We are advanced. That's why I told you there's no book in the nation or in the world that can challenge you. That's why I had to write all the problems. All right, today we are looking at what we call arguments. Now here is the most famous argument there is in logic. P implies Q. P, therefore Q. This is called an argument. An argument is made of these statements above this line. We call these statements the premises. And then we have a line, and you guys know that this symbol means therefore? You guys seen that before? This thing here is called the conclusion. Okay? These are the premises, this is the conclusion. So what is a valid argument? A valid argument means whenever these are true, that will be true as well. That's what a valid argument is. It's a logical, this is a logical conclusion based on these 2 premises here. So what you have to do in number 1 of tonight's homework, you have to show that if an argument is valid or invalid. Okay, and it says by making a truth table. So to show that an argument is valid, there are 3 ways to do it. Okay, I'm going to show you all 3. Here's the first one. We're going to make a truth table for this. So this is what you do. You make a truth table for the first premise. Then here's the second premise, make a double line, and then you put the conclusion right there. So just make a truth table. P is always what? True, true, false, false. Q is always true, false, true, false. And then, have we memorized this one yet? Or we can wait for Monday morning? Because this is this gonna be on the quiz? Yeah, this is on the quiz. What is it? True, false, true, true. Correct? Remember, the only time it's false is when the first one is true and the second one's false. Okay, so again, what is a valid argument? Whenever the premises are true, the conclusion is also true. So, what lines, there's 4 lines here. Which lines do I have both premises being true? Look, I'm pointing at it right there. Right there. When they're both true, does the conclusion come out true?
Yeah.
Yeah. Therefore, this is a valid argument. See, if that came out to be false, then we say that this is an invalid argument. But why would this be the most famous argument in logic if it's not valid, right? Anyway, this argument has a name. We call it Modus Ponens. So, Modus Ponens, it doesn't matter the meaning of the words. You look at the form. Gorilla implies banana. Gorilla, therefore banana. Or would you rather work in shapes? Box implies triangle. Box, therefore, triangle. Yeah, I'd rather have the gorilla and banana. So that's how you show an argument is valid. Okay, let's do it. The second most famous argument in logic. P implies Q. Q implies R. Therefore, okay, using your common sense, what do you think the conclusion, a logical conclusion would be? P implies R. Okay. Now, what if I tell you to show that this argument is valid by making a truth table? What would you do? You do exactly what I taught you here. Put the first premise, P implies Q. Put the second premise, Q implies R. Make a double line, and then put the conclusion, P implies R. Now, how many lines are there going to be in this truth table? There's going to be 8 because you got P, Q, and R, right? Okay, now, are we good enough to fill it in? Because you guys made lots of truth tables with 8 lines in it already, right? So remembering that P is true, 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 false, 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 false. Q is true, true, false, false, true, true, false, false. And R is true, false, true, false, true, false, true, false. Fill it in, Lou. Impress me. Or do I have to write training wheels on the side?
No, you don't.
Okay.
True.
50-50
False.
chance every time.
No, true, false. True, true. True, false. Okay, true, true. True. Wait, no, sorry, I'm not here, right?
Okay, you know what? Okay, based,
Oh yeah, that's right.
time out. Based on what I just seen, we need to draw the training wheels in. So, no, don't be afraid to use training wheels. Just don't let your neighbors see you. You put it out. So, so what's the training wheels? True, 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 true. Oh, no, I don't know why you guys are scared of training wheels.
You don't want to use training.
Okay, I'll give, look, on the quiz on Monday, I actually gave you the training wheels. I wrote it in for you. But then by the time you get to the test, no need training wheels, right? Quiz, no, quiz, you might need training wheels. Test, well, if you want to draw it in, to draw it. How long? It took me like, what, 10 seconds to do that? No, more like 15. Okay, did Lou get it correct?
Yeah.
No.
Oh, what? No.
No, you didn't. So, P implies Q, so this implies this. Remember, the only time a conditional statement is false is when the first one is true and the second one is false. So what is this? True, true, false, false. And when the first one is false, you know it's true already, right? We talked about that. See, that's why we need training wheels. Otherwise, see, this would be a fatal error on the test. -8 out of 8. Well, because you did it wrong.
No.
Okay, Q implies R now. Okay, here. Q implies R. Look. True, false.
True, false, true. That's what I was doing.
You did the wrong line. Pick up double, -16.
Oh.
True, false, true, true. True, false, true, true. And then finally, P implies R. Okay, you guys got that? No, just copy it down.
Nah.
Copy it down. Okay, now how do you determine whether the argument is valid? Whenever the two premises are true, the conclusion has to be true every time. So what lines in the truth table do I look at? Where are the two premises true? Here. Anywhere else? Here. Here. And there. There are 4 lines in the truth table where the premises are true. And in each case, does the conclusion come out true? Yes, so this is a valid argument. If just one of these came out false, if just one of them were false, it would be an invalid argument. So you guys understand what a valid argument is? Whenever the premises are true, the conclusion has to be true every time. So this is a valid argument. And why would I teach it to you if it was the second most famous one? You know what we call this? This is called the Law of Syllogism. Some books call this the Law of Transitivity. You know why? transitivity. Because doesn't that remind you of the transitive property of equality? What's that? Does this look familiar from Algebra 1? If A equals B and B equals C, what can you conclude? A equals C. This is called the transitive property of equality. Remember all of those properties you learned in Algebra 1? Oh gosh. Like what is this? A plus B is equal to B plus A. The commutative property of addition. Remember all of those properties? Apparently not. What about this? A plus, oh, let's do times. A times B times C is equal to A times B times C. That's called the associative property of multiplication.
How do you remember that?
Because I went to kindergarten.
Oh. Can you understand that?
What?
Associative.
Well, some teachers go, see how you associate? Like, doesn't matter what order you do it in. Okay, whatever. Okay, what are we talking about here? Okay, let's move on. Prove, okay, so here, now you gotta know the second, oh, actually, I don't have a problem that does the second method. I gotta change that. Okay, now there is a second method to proving whether an argument is valid or invalid. Does everybody understand this technique? Okay, second technique, this is all in your notes. In fact, why don't we still do Modus Ponens? I gotta erase this. Okay, here's Modus Ponens. Okay. What if I ask you to prove that this is a valid argument? Are you guys looking at your notes?
Yeah.
What's the second way? Prove that this is a valid argument by showing that the conjunction of the premises implies the conclusion is a tautology.
What?
Oh gosh. Okay, look at the notes. It says valid
Oh,
argument.
yeah.
Validity.
Oh.
There, look at B. Showing that the conjunction of the premises implies the conclusion is a tautology. Now you got to understand the words. What does conjunction mean? Oh gosh. What does, let's one word at a time. What is conjunction?
Something like thinks of other stuff.
It's an and statement. Conjunction, look. If we don't know that conjunction means and disjunction means or by now, we're in trouble. Look, this is the way I was taught. Conjunction means and. Disjunction means or. What's the problem? What's the problem?
What if you mess up where you
Oh, so you're saying, oh, what if you think conjunction is or, and that's and?
Yeah.
That's wrong, that's why. Do I have to tell you guys everything? That's a joke, people, if you didn't figure that out. It's a joke. You just gotta know, or you figure out some convoluted method to figure. Now I forgot what I'm talking about. Okay, the conjunction of the premises implies the conclusion is a tautology. Now what the heck is a tautology? Did we discuss that yet? We should have, because in last night's homework, oh, I can't scroll. You know in number 1 on last night's homework, the last one, number 1, 1G, whatever,
Yeah.
didn't it come out true, 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 true?
Yeah.
What do you call a statement that comes out true every time? A tautology. It's in the notes. And then what do you call a statement that comes out false every time?
I don't know.
A tautology. No, it's called a contradiction. You guys just like to make up your own words, yeah?
Pretty much.
So a tautology is a statement that comes out true every single time. In fact, how many of you have seen the movie, what's that movie where they kill Osama bin Laden?
Oh,
Zero Dark 30. How many people saw that? 2 people. Okay, that's 2 more than the other class. Did you guys notice that when you watch the movie, they said the word tautology? No. Okay, so they were gathering information on where they thought he was, and then we don't know what we don't know. You remember that?
We don't
Yeah.
know.
We don't know what we don't know. And then somebody said, you know, that's a tautology. It's true. Think about it. We don't know what we don't know. Yeah, it's true every time. It's a tautology. Anyway, a tautology is a statement that comes out every time. So, another technique to show that this is valid, the conjunction of the premises. These are the premises. What does conjunction mean again? And. So, the conjunction of the 2 premises implies the conclusion is a tautology. So, if you make a truth table for this, and it comes out to a tautology, then the argument's valid. But I don't have to do that because we already did it, right? Last night's homework, 1G.
Oh, wait, why would you use this one over the other one?
Because on the test, you're gonna have to show me all three. I'm gonna tell you which technique to use.
Oh.
You're gonna do all three.
Oh.
You can't just pick your favorite one. I'm gonna make you do it. Okay, Mr. Park, I just gonna do the first one. I'm gonna leave the other two blank. Then that's a -8, -8. You're already down to what is that, 84, when the class average is 95.
Oh.
But you can do what you want. Some people, 84 is good. But that's assuming the rest of the test is all correct. Okay, now, the third method. The third method, read it. It's called indirect proof. Some of you are gonna like this. This is probably the favorite one here. How much time we got? Oh, we're in trouble. Okay, so look at number 2. Prove that modus ponens and the law of syllogism are valid by indirect proof. I will do A for you. I'm gonna do modus ponens for you. So, P implies Q, P, therefore Q. Prove that this is a valid argument, so this is the third technique, by using indirect proof. Now, what the heck is an indirect proof? Okay, I will tell you. So, in order to use an indirect proof, you have to understand what a valid argument is. If this is true and this is true, this will also be true, right? That's what a valid argument is. When this is true and this is true, the conclusion is true all the time. So this is what an indirect proof is. We're going to suppose that this is false. Okay? So your first sentence in an indirect proof is always going to be, suppose whatever your conclusion is false. You're going to suppose it's false. Oh, what do you mean? What do you mean the first sentence, Mr. Park? That's because an indirect proof is a paragraph. You have to write a paragraph. Okay. Oh gosh, here we go. That's what you know when if you go to college and you major in mathematics, all the proofs are paragraph proofs. You just write paragraphs, man. That's what upper level mathematics is. In fact, in one of my courses, all we did the whole semester was just prove 100-something theorems. What? That's what it is. College math is way different from high school math. High school math, you're actually computing things, yeah? But in college mathematics, everything above calculus, you're doing proofs. Okay, anyways, getting back to this. So whatever your conclusion is, let's suppose it's false. Now, why don't I just do the proof, and you can see how it works. Now, you got to remember now, this is a true statement, this is a true statement, then this has to be true, but we're supposing that it's false instead. Okay? So your goal is to come up with some kind of contradiction. So if Q is false, and this entire statement is true, what conclusion can you make about P?
It's false.
P has to be false, right? Because if P were true, if you have a conditional statement where the first one is true and the second one is false, doesn't that make it false? But we know it's true. So therefore, P has to be false. So we say, then P is false in premise number 1. Everybody understand that? If Q is false, in order to make this entire statement true, P has to be false as well. Otherwise, it wouldn't be true. Now, your goal is to come up with a contradiction. Does anybody see a contradiction here? This one's really easy. Look, we figured out P is false, but look right there. P is true. That's a contradiction. So, when you get a contradiction, you're happy. That's the goal. Contradiction. P cannot be both true and false. How can you have a statement that's both true and false? No can. That's the contradiction. Therefore, the argument is valid. There you go. This is an indirect proof.